Okay, so let's look at some actual spectra with that behind us. Here's a very simple spectrum, chloromethyl methyl ether. This is an ether. How many chemically different types of hydrogens? Two. You see two resonances in the NMR. Well, you see two resonances, one at around 3.5 and the other at about 4.5. That's due to the fact that you have two electron withdrawing groups of chlorine and an oxygen. So the one to the left is the CH2, and you can tell that by the size of it. It's not integrated in that it doesn't show you the areas underneath the peaks. When you have a test, the spectra will show you the areas underneath the peaks. So the one on the left is the CH2, and the one on the right is the CH3. Very easy. Okay, so this here is also just going to show two peaks. The CH3 is this peak right here because it's next to the carbonyl. The CH2 is a little further to the left because it's got two electron withdrawing groups flanking it, the Cl and the C double bond O. And if this were integrated to give the areas, you would see that it's 2 to 3. Now, you wouldn't be able to tell if this is chloroacetone. There's not enough information there. A spectrum can be too simple. There's just not enough data there to tell that it's chloroacetone. This is where mass spectrometry would come in because it would give you the molecular weight of the compound. And you would figure out this is C3H5ClO. You could tell there's a chlorine from the mass spectrum. Mass spec is very good at detecting chlorine and bromine. You'd figure out the degrees of unsaturation. It would come out to 1. By looking at the infrared, which shows you functional groups, you'd see that there's a carbonyl, and then the NMR would finish it off. So you need some more information. But certainly the NMR is easy enough to interpret. Here's an aromatic compound, as we call it, benzene ring, and then CH2 and Cl. It's actually called benzyl chloride. See this peak between 7 and 8 parts per billion? That's the dead giveaway for hydrogens on a benzene ring. Now, very important point. The areas are not here, but if they were here, the hydrogens on the benzene ring are 1, 2, 3, 4, 5. They're all showing up here. The CH2 is 2 hydrogens, so this would integrate 5 to 2. 5 hydrogens in the aromatic region between 7 and 8 means a monosubstituted benzene ring. Can't be anything else. Monosubstituted means just one of the 6 hydrogens that you would have in benzene itself has a non-hydrogen substituent, in this case the CH2Cl. But there could be up to 5 other substituents on that benzene ring. So if you had a di-substituted, there would only be 4 hydrogens left on the ring. And the area for the benzene peak would be 4. So 4 means di-substituted, 5 means monosubstituted. That's very important. And then from the relative area, you can tell how many hydrogens you have here. Now this peak is not actually a singlet. If you were to expand it, you'd see that it's a very jagged multiplet because these hydrogens on the benzene ring are not all the same. The ring is flat. These 2 hydrogens labeled A are twins flanking the CH2. Those are actually called ortho hydrogens. This pair right here is also identical, but a different set of twins. And this one all the way across from the CH2 is the 3rd chemically different type of hydrogen. There are actually three chemically different types of hydrogens on a monosubstituted benzene ring. The two flanking the substituent, the two flanking but one carbon back, and the one all the way across the ring. And I say that because you won't always see what looks like a singlet here. That only looks like a singlet because the spin-spin splitting is very fine, and it's not able to resolve the spaces between the multiplet. Yes.
How many chemically different hydrogens are there?
Three.
There's three?
Yes.
So it's the two twins and the one and the horizontal twin?
Benzene rings are flat, like a penny. So if you look at the two hydrogens that symmetrically flank whatever that substituent is, they're twins. They're chemically equivalent. So you see one particular resonance for that. But these hydrogens, which also by symmetry are twins, are different from the A set of twins. So they represent a second chemical type, and then this hydrogen here is actually a third chemical type. And they're capable of splitting each other even across the ring. I always presented spin-spin splitting to you as a neighboring hydrogen thing. Benzene is a whole different planet from other organic real estate. And hydrogens on a benzene ring can talk to one another completely across the ring. So you can get some very, very complicated spin-spin splitting patterns. Do not even think about it. Don't bother to interpret it. Just look at the fact that you have absorption between 7 and 8 and how many hydrogens. If it's 5, it's a monosubstituted. If it's 2, if it's 4, it's a di-substituted. I think I have one here that shows spin-spin splitting there. Well, you can sort of see it here. This is the peak for, this is a monosubstituted benzene ring. All of the hydrogens on the ring are appearing between 7 and 8, but you can certainly get the sense that if you were to blow this up, and you can, when you're sitting in front of the instrument, you would see maybe a dozen different peaks all jumbled together. It's just unresolved at this magnification. And then this is an isopropyl group right here. We've looked at that before. The CH3 hydrogens are a 6-hydrogen doublet right here, because as a group, they all have one neighboring chemically different hydrogen, HB, right here. And then HB has a total of 6 equivalent neighbors, so the N+1 rule produces a multiplet of 7 lines. And it shifted a little to the left because a benzene ring has a slight electron withdrawing effect, sort of like an oxygen or a chlorine. And this would integrate to 6 hydrogens. The doublet would integrate to 6 hydrogens and the heptet to 1 hydrogen. So 6 is 2 times 3 or 2 methyl groups. Remember, use logic, simple logic. It's not 6 totally unrelated hydrogens. That's 2 methyls sitting on the same particle. And then that 1 hydrogen is obviously split by all of those, so that's an isopropyl group attached to a monosubstituted benzene ring, which would integrate to 5 hydrogens. Go back up here. Hey, here's that ethyl bromide that I talked about before. You can see the CH2 next to the bromine is right here. The bromine has a strong electron withdrawing effect and shifts the peak to about 3.5. The CH3 peak is around 1.6 or 1.7. if I highlight a little bit, it does see the bromine, but only a little bit. Certainly not as much as the CH2. But this would be 3 hydrogens by area, this would be 2 hydrogens. The triplet quartet would say it's CH3, CH2. What you would not know is that there's a bromine sitting here. You would know there's something electron withdrawing there, but it could be a bromine, could be a chlorine, could be an oxygen. So you need other data, and there would be. That's why people who have NMRs also always have infrared spectrophotometers and mass spectrometers to fill in that information.
Is this the Blackboard?
Is it what?
Is this on Blackboard?
Yes, these spectra are, but the best thing to do is to use the SDBS database. I mean, you go to that factory where that is. Okay, so if you go to your search engine, let's say it's Google, and just type in SDBS, that spectral database, it will take you to this free online spectral database. Okay, and you don't have to sign in, you do have to agree to not abuse it by downloading Spectra. But you get a very nice user interface that allows you to look at spectra based on either the name of the compound or a molecular formula or a molecular weight, any information that you have. So if I wanted to look at, say, ethyl bromide, now the problem with searching by name is, as I mentioned, you've got to get it right. So does this database have it as ethyl bromide or bromoethane, which is the IUPAC? We'll find out. Okay, so it's good enough to cross-reference that. And because I didn't use the IUPAC name, it's a little confused, but you can see ethyl bromide is the 4th one down the list. And I can see for ethyl bromide, either the mass spec or the CNMR or the HNMR or the infrared. So if I click on HNMR, there's the HNMR of ethyl bromide, just as we were looking at before. In fact, that's where that spectrum came from. So you can learn to interpret spectra by just looking at spectra of known compounds and saying, does that make sense? Now, it actually will interpret it for you. You go down, scroll down further. It'll give you the assignments for the hydrogens. So even a very complex molecule, it will label, this is this hydrogen, etc. It won't sort out the spin-spin splitting for you, but it will tell you which hydrogen goes with which hydrogen in the spectrum goes with which hydrogen in the compound. Okay, so use that. These spectra that I'm showing you are on Blackboard, but this also will help you. And there are other tutorials online that you can use. Let's see what else we have here. Okay, good point here brought up by this spectrum. NMR only shows you chemically different types of hydrogens. if your molecule has symmetry in it, you can be fooled. Take this compound right here. You notice it has a plane of symmetry right through the middle. So the two CH2s in the middle are twins, and the two CH3s on the ends are twins. So how many chemically different types of hydrogens do we have? Two. Look at the spectrum and you see two. They're close together because they're all pretty much the same type. CH next to an oxygen. But they are separate, and the areas, if you had the integration data, the B hydrogens, which are represented by the P to the right, would be 6 to 4 for the A hydrogens in the middle, because you have 6 methyl hydrogens and 4 methylene hydrogens. However, the NMR would not be able to pick up that it's 6 to 4. It's going to tell you that it's 3 to 2. All it gives you is the lowest whole number ratio of hydrogens, and that's 3 to 2. It only sees 2 chemically different types of hydrogens in a relative area ratio of 3 to 2. How do you translate that into 6 to 4? Not so easy. You're looking at only half of this molecule in the HNMR. Now, some of it would surface as you try to come up with solutions. Because the 3 to 2, you have to say, well, that's 5 hydrogens, CH3, CH2, and then that's the end of the hydrogen, so what do I put there? If I put a chlorine, well, I'm going to have a quartet and a triplet. If I put an oxygen, if you put anything there, you're going to have a quartet and a triplet. How does it come out that you have CH3 and CH2 and they're all singlets? If you try piecing sensible molecules together, you'll constantly come up against a brick wall. And that's something that you have to do with an NMR spectrum, is sometimes bang your head against a brick wall for a long time. I've sat with spectra sometimes for months trying to interpret them. The more complicated the molecule, the more difficult it is, but also sometimes the simpler the molecule, the more difficult it is. There's a sweet spot in the middle. So this is too simple. Now, mass spec would help you here because it would give you a molecular weight. And you'd know that there's a lot missing here. Based on the molecular weight, you'd quickly figure out that it's double that. It's not 3 to 2, it's 6 to 4. And you'd be home free. But watch out for symmetry, it can fool you. Well, okay, so here you see 5 hydrogens on the benzene ring between 7 and 8, or I'm telling you it's 5. And then the 2 CH2s are splitting one another into a pair of triplets. Those 2 CH2s in the middle are different. And then the OH is there at 2 parts per million. In addition to having the OH, in addition to having a variable chemical shift, also sometimes does not cause spin-spin splitting with neighboring hydrogens. Because the way the hydrogen jumps from one oxygen to another interrupts that spin-spin chatter that goes on that causes spin-spin splitting. So OH is tricky. You could have seen a triplet there, but you don't. It's basically a singlet for the OH. But that would be easy to interpret. 2 triplets like that means CH2, CH2, where the 2 CH2s are chemically different. And each CH2, by its chemical shift, is a little off to the left, which means that there's something electron withdrawing next to it. In one case, it's the benzene ring. In case of the other one, it's the oxygen. Yeah.
when you had asked, like, how many or how many different chemical hydrogens are attached to that B, there's two, correct? The hydrogens are
Well,
on the.
no, chemically different hydrogens belong to the molecule. How many chemically different hydrogens do you have in this molecule? Allowing the benzene ring to just be one type. They're not technically, but just always say they're one type of hydrogen. So how many do we have? 4. Right. That's all that means. So you should see 4 resonances, and you do.
No, I'm talking about in terms of the resonance, it's a triplet.
That's separate.
Yeah.
A resonance can be a singlet, doublet, triplet, 7 lines, 10 lines. It's all one resonance. It's just visually or cosmetically split into a multiplet because of this spin-spin splitting phenomenon with neighboring hydrogens. So the BCH2, ignoring the OH, which is not causing any splitting, is next to the C hydrogens. So B has 2 chemically different neighboring hydrogens, n plus 1 is 3, so you see a triplet. Similarly, and this is reciprocal, C has B as 2 chemically different from itself neighboring hydrogens, and so that also appears as a triplet. So you get a pair of triplets. And notice, by the way, how they kneel in towards each other. And NMR spectroscopists call it kneeling. The triplet is not a 1-3-1 symmetrical pattern. They lean in towards each other. So when you see that, those 2 multiplets are reciprocally splitting each other. Yes.
How do we, if the hydrogen for OH is jumping all over the place, how do we know that it's gonna be an OH? Like, is there any sort of clues besides,
Nice.
I mean,
You don't.
no?
Origami.
It could be a CH all by itself. Right. That's why I say it helps to have mass spec and infrared. In infrared spectroscopy, an OH just hits you right between the eyes as soon as you look at it.
If you saw that little broad kind of.
Yeah, then I would conclude that it's an OH.
Okay.
But if it looks sharp, you really don't know.
Yeah.
Now, there is an experiment you can do, which is to add a drop of D2O in water, in which case deuterium starts exchanging for all the OHs, and that peak will jump, and some of it will disappear. That's a dead giveaway for an OH, but infrared spectroscopy is better. Anybody can see that you have an OH just by glancing at an infrared spectrum, and we'll get to that. So there's some missing here. Okay, let me switch to carbon now. We need to look at that quickly. Once you're familiar with hydrogen NMR, carbon NMR is really quite simple. Okay, here are 2 spectra. The bottom one is a hydrogen NMR. How do I know that? Well, if I look at the scale, it's cut off here, but let's look at the scale. See, the scale runs basically from 0 to 10. Whoever ran this just didn't like to do that. It actually runs from about -0.5 to 11. But that's clearly hydrogen's NMR scale. The top one, notice that it goes to about 200 ppm. That's a carbon spectrum. Hydrogen runs basically 0 to 10. Carbon runs 0 to 200. Now, I'm telling you this because they're never labeled. You're just supposed to know what you're doing, and if you're looking at a spectrum that runs to 200 parts per million, you obviously are not going to interpret that as a hydrogen NMR. The spectrum at the bottom shows a complicated set of peaks between 7 and 8, and then what basically looks like a quartet and a triplet up to the right. All of that jumbled set of lines between 7 and 8 refers to hydrogens on a benzene ring. And if you were to integrate it, would integrate to, I don't have the answer, propiophenone. Propiophenone is this compound here. Benzene ring, C double bond O, CH2, CH3. So between 7 and 8, that would integrate totally, for all of those jagged lines, to 5 hydrogens. Now that really splitting apart into 2 sets of jagged lines, and the fact that you see all those jagged lines, is what sometimes happens. Particularly if you have a C double bond O attached directly to the ring. There's an interaction between the pi system of the carbonyl and the pi system of the ring that kind of brings these hydrogens to life as chemically different hydrogens. So as I said before, don't worry about that. It's clearly a set of hydrogens in a benzene ring, and all that matters is the area. If it's 5, it's a monosubstituted benzene ring. And then you have a CH2, CH3. And you can see where that comes from. You have an ethyl group, the CH3 is a triplet, the CH2 is a quartet, and then the C double bond O separates the ring from the CH2, CH3. Now, that molecule, saying that all the hydrogens on the ring are lumped together, has how many different kinds of hydrogens? The hydrogens on the ring is one set, and then how many other types? 2. So a total of 3 chemically different hydrogens. Now, for carbon NMR, you have to be able to look at that compound and identify how many chemically different types of carbons there are. Different question. In carbon NMR, you don't see hydrogen at all, you see carbon. So for propiophenone, how many chemically different types of carbon are there in this molecule? Well, obviously, 1, 2, 3. Then there's the issue of the benzene ring. How many chemically different carbons do we have on the benzene ring? Technically. 4. That carbon where the substituent is unique. That, in fact, is called the ipso carbon, IPSO. And then you have a pair of what we call orthocarbons that are twins, but different from the ipso carbon D. And then another pair of twins up here, and then that unique carbon all the way across the ring. So a monosubstituted benzene ring has 4 chemically different types of carbon. So 4, 5, 6, 7 is the correct answer. This is not so easy to do. I always ask this on a test for a molecule, and a lot of people just blow it. It's just a matter of looking and practicing also ahead of time so that you're not fooled. Don't be fooled by symmetry, and don't be fooled by a benzene ring. Okay, so what does that mean in terms of carbon NMR? Well, what you're supposed to do then is assume that in the carbon NMR, you will see 7 resonances, one for each chemically different type of carbon. Let's see how many we have. two on the far right, one on the far left. The two on the far right are A and B. Ordinary, like methyl hydrogens appear at around 10, which is where that first peak is, just next to 0. And then the C double bond O is right next to the B carbon, so that shifts it down to around 25. So you see the same chemical shift effects. And then they cluster between 120 and 140. Those are carbons on a benzene ring. So the region that's 7 to 8 in the HNMR is 120 to 140 in the carbon NMR. Carbons on a benzene ring come in that region. Carbonyl carbons are really distinct. They appear around 200 parts per million, and that's what that peak is on the far left. Now, you say, well, do I have 4 peaks there in the aromatic region? Yes, you do, because you can clearly see that there are 3, but the bigger one actually is 2 peaks. And you would see that if you expanded the scale. This is a 200 part per million window squeezed into the same dimension as a 10 peak window. So you can expand this as big as this room, and you will see a foot between the 2 peaks that now are sitting on top of one another. So this is just a visual problem, because we're trying to squeeze the spectrum on an 8.5 by 11 piece of paper. But that's not a real limitation. There are 2 peaks there, and you would be able to see that in the real spectrum. Now, you don't see any spin-spin splitting in the carbon-13 spectrum. That's normal. The spin-spin splitting that does occur between the carbons and the hydrogens is erased by a technique called decoupling. It's a fairly sophisticated electronic technique, but we're able to essentially decouple all the hydrogens from the carbons. Because if we didn't do that, that spectrum would be so complicated that you'd never interpret it. The spin-spin splitting, so here's the C13 that we're looking at. A carbon-13 would be split not only by a chemically different neighboring hydrogen, but also by any hydrogens directly attached